author of Manning's new book, Refactoring to Rust, which is currently in early access. And today we are going to be creating a very simple TCP chat server using the Rust programming language, its async await features, and the Tokio concurrent programming library. So we should be on the stream for about an hour today, and I plan to be programming for most of that. There are a couple places where they'll have sort of natural breaks for questions, but please feel free to ask any questions that you have just in the stream chat whenever they come up, and I will address those as soon as I see them. I do have a second screen down here that has the stream chat up, so I will try to look at that as frequently as possible and address those questions as soon as they come in. So before we get started, let's talk about what we're doing today. So Rust, as I'm sure you're aware, is a programming language created at Mozilla several years ago in order to allow developers to create really fast programs that operate close to the metal while sort of saving developers from a lot of the very common memory safety pitfalls that languages like C and C++ have. So Rust is very high performance, very low overhead, but it also has compile time guarantees that save us from doing things like use after free errors, dangling pointers, all this kind of stuff. And the other piece here is Tokio, which is a Rust library that allows us to do asynchronous I/O and other asynchronous operations in Rust code. So when we say async, it's generally only talked about in contrast with synchronous code. So you have synchronous and asynchronous, two sides of the way that you can do operations. So basically, when you have a synchronous operation, that might be something like reading from a file, sleeping in a timer, reading off a network stream. And so when you have an operation like this, that is going to basically block your entire thread's computation. It's going to just sit there. It's going to do nothing. And, the OS will probably schedule some other threads to run on your CPU while that thread is waiting for something to happen. We contrast this with asynchronous computing, where we actually do these kind of context switching operations inside of our application's code. We maintain state in our application code that allows part of our application, be that a runtime or some kind of scheduler event loop, to swap out different operations and suspend them when there's nothing to do, and then resume them once there is some resource or timer or whatever that's ready and good to go. So Tokio, as I mentioned, is a library which allows us to do these kind of asynchronous operations in Rust. And it has a ton of different features in it. It has timers, file I/O, subprocesses, network modules, everything that can and might block in a normal program. Tokio has a facility for doing in a way that is asynchronous and non-blocking. Tokio is used very, very widely across the Rust ecosystem. It's used at some huge companies, Google, AWS, Microsoft, Azure. I use it in my day job at OneSignal. We are hiring. If you're interested in a job working with Rust, send me an email, nate@onesignal.com. Tokio is a fantastic library. It makes it super easy to write really high performance networked applications with Rust and async computing. So today we're going to be making a very simple chat server, and basically this is just going to allow multiple TCP clients to connect up to the chat server. When one client sends a message up to the server, the message will be broadcast to all of the different clients that are connected. So we can have a really, really simple chat session that's going on. Yeah, so are there any questions from anybody on the stream about anything that I've said so far? don't see anything. So we're going to just jump right ahead. Once again, if you have any questions at any point during the stream, please just dump those in the stream chat as soon as possible. And I will answer those immediately as I see them. Very willing to be interrupted. So do not shy away from that. Also, I want to point out there's a discount code at the top of the screen for my book, Refactoring to Rust. Refactoring to Rust is all about how you can take code that's written in non-Rust programming languages and actually swap out the performance critical or memory safety critical piece of your code and rewrite just that tiny little piece in Rust while keeping your larger system intact. So it's not always feasible to rewrite an entire application in a new programming language. That's a very often touted thing as good to do. However, it's very often that you underestimate the complexity of that. And what may be much more impactful is actually taking that very small piece that has a big performance impact and just swapping out that piece. And that is what we talk about in my book, Refactoring to Rust. So if you'd like to check that out and get 40% off that, there's a discount code at the top of the screen there, TWITMERA40. So check that out on Manning's website, manning.com. So without further ado, we can go ahead and jump into the coding. So if you've written absolutely any Rust before, you should recognize this. This is the standard Hello World program that you get when you start a new Rust project with Cargo. So this is totally blank project. There's nothing in here at all except the Hello World. So before we start writing any Rust code, we're going to need to add in one additional library, which is, of course, the Tokio library. So I'll just drop that in my Cargo TOML file. And you may not be familiar with this exact syntax if you've not been using Rust for a super long time, but Rust has conditional compilation flags that you can use to trigger different features in libraries. And basically what this allows you to do is Tokio basically is a very large library. It has lots of features, lots of things that you might not need in every single program. So for example, if you're making a web server, you probably don't need to have Tokio's sub-process module turned on. So these conditional compilation features allow you to control which things are included and which things are not included. For our purposes, we are enabling everything because I don't feel like enumerating them for this stream. But this is just including version 1 of Tokio with every single feature enabled. Great. Now that we have Tokio included as a library, we can start writing some Rust code for our async chat server. So before we can start writing any functional code, actually, we need to make some slight edits to our main function. So right now it's a normal main function that works with any old Rust program. We actually need to turn this into an async main function. And immediately after doing that, we are confronted with what will probably be the first of many compiler errors that we'll run into, the compiler trying to help us out and stop us from generating an invalid program. Main has an invalid return type, impl future. So by default, the Rust programming language has no idea how multiple asynchronous computations should be interleaved with each other, basically how they should be executed. So in order to actually run any async computations, which Rust calls futures, we need to provide Rust with an executor, a thing that knows how to run a future and drive it to completion. So a future is basically a value that does not have, it's basically a thing that does not have a known value yet, but it may have a known value at some point later on down the line. So this might be, a network read request, or so let's say an HTTP request. You send a HTTP request to, get google.com. you're not going to know what comes back from that for, maybe 100 milliseconds. So as soon as you send that request, immediately you'll get a future back, and that future will just be in a pending state where it's waiting for the network transaction to complete. And then eventually that network transaction will complete, and your future will be in a completed or a resolved state. So basically, we need to create a main function, and Rust is basically just going to take our async function and wrap that up into something that returns a future with a lot of compile time magic that actually generates a very efficient state machine for us. However, as I mentioned, Rust does not know how to run a future by itself. It knows how to generate futures. It's great at generating futures, but it does not know how to execute a future. So the way we can fix this is there's a procedural macro that's available from Tokio called Tokio main. And I can wrap the main function in Tokio main. And basically what this does is it takes our async main function, which is typically invalid, and turns it into a normal main function with some Tokio stuff inside of it. But this just saves us a little bit of boilerplate code writing. So if we try running this program now, it works exactly the same as a normal hello world program in Rust does. There's nothing special or magical or weird that's going on just yet. So we get our hello world on the console just like we expect. So that's great. So we're not going to go straight from hello world to having a chat server. There's going to be some incremental steps that we're going to need to take. And the first incremental step that we're going to take is to make a TCP echo server. So basically, this is a server that will sit there. It will wait for a client to connect. And once a client has connected, it will take any message the client sends and bounce it right back to the client. So just like the echo program, echoes any message that you send to it, the TCP echo server is going to echo any message that it receives right back to the client. So let's go ahead and create that. The first thing that we're going to need is a TCP listener. Now this is a type that's coming from Tokio, and it's it's basically just going to sit there listening for incoming connect requests on the port, and and it's going to allow those clients to connect. So if I look at the return type here of TCP listener bind, we can see that it's a impl future, and the output type is result TCP listener error. So because this return type is an impl future, if I want to get to this result that's inside of the future, I need to use .await to get that result out. So we can now see that we are getting that result out there. And await is a Rust keyword that tells the Rust compiler, hey, when you get to this point, you're allowed to suspend this function until this future that's on the left side of await resolves and is ready and has an item that's available to do some processing on. So await, very similar to Node.js or C# or any other language that has await. In Rust, it just means suspend this current task until our future is ready to be acted on. So now that we have await there, and this is giving us back a result, I will add unwrap for some very basic and not great error handling. So we have a TCP listener, and we are ready to start accepting connections. So if you've done any kind of socket programming before, you will probably know what is coming next, which is to call the accept method on our TCP listener. Accept is a method very similar to how it sounds that, whoops, sorry, this is not socket, it's listener. Accept is a method that accepts a new connection from a TCP listener and yields the connection as well as the address of the connection. So similar to bind, accept returns a future, and that future outputs a result. So I will have my await unwrap on there. So we can see now that we have a socket, which is a TCP stream, and we have an adder, which is a socket adder. We're not going to use the address for now, so I'm going to underscore that so I don't get unused warnings. And we have our socket. Now, if I were to run this program right now and try connecting to it with a telnet client, telnet localhost 8080, we can see the connection is accepted and then immediately closed, and our Rust program, it exits. Because of course, we set up a TCP listener, we accept a single connection, and then we exit. There's nothing else that happens afterwards. So what we're going to need to do now is we're going to need to read something in from the client, and then we're going to need to write that same thing back out to the same client. So if we want to read some new data into memory from a network stream, we need a little buffer to put the data into. So I will create a buffer in the form of a stack array. It's just 1 kilobyte, 1024 U8s, or 1024 bytes. Go ahead and create that, and then I can call socket.read. And this, again, is an async function. So it's going to suspend execution until the read has finished, and it's going to return a result. And this error that we're receiving now is because read is actually associated with a trait in Tokio, the async read ext trait. And that's because all the items in Tokio that implement their async read trait, they just want to implement a single item. For example, the socket, it just implements a method called, I think it's poll read. And then this wrapper trait, async read ext, actually has all the things that end users of the library might want to use to do higher level read operations. So this error cannot borrow socket as mutable is very easy to solve. Of course, we just need to declare our socket variable as mutable, and now this is going to compile. And then socket.read actually returns the number of bytes that were read from the stream onto the buffer. So the buffer has 1024 bytes on it, has space for 1024 bytes to be read into memory. However, we might actually read a lot fewer than that when we call socket.read. So we need to use this bytes read to truncate our buffer when we send it back to the client. So to send back, I'm going to use socket.writeAll. And a common confusion point with writeAll is it does not write a message to every socket that is connected to a TCP listener. Instead, it writes every single byte that is in the input buffer out onto the output buffer. So it's very common, especially when you're not writing naturally async code like you have with Tokio, to use just write instead of write all, and then to actually intercept calls to write that would naturally block, and then to do your own kind of scheduling with write calls to make sure that you never block any of your IO threads. Since we have Tokio doing that for us, it's not necessary. We can use write all, and we can not worry about having to manually advance our own cursors or things like that. So I'll pass in buffer and up to the number of bytes read. Dot await, dot unwrap, fun. And then similar to the read ext trait, there's an async write ext trait that I need to import in order to get write all to work. So now if I run the server and I connect a client, I write hello, we can see now it is actually staying alive, and I can write hello here. And if I hit enter, this is the hello that I typed, and then there's a hello that comes back from the server. So all seems to be working exactly as expected. Very nice. However, maybe we want our echo server to support more than one message at a time. Like right now, it just operates on one message and then it exits, and we have to restart the server. So not only can we not have more than one client, we can't even have more than one message. Extremely limiting, right? So a great first incremental step is going to be to make this support multiple messages sent at a time. So we can do that by adding an infinite loop. So as soon as one client connects, we'll drop into this infinite loop and we'll start reading messages and writing them out. So I can go ahead and recompile, rerun that. Hello. How are you? Excellent. So we have our very basic TCP echo server is reading messages, writing messages, more than one message at a time it can handle. So I'll go ahead and exit that now. And there's another change that I would like to do here. So right now we have this buffer that we're managing ourselves, and we're truncating it before we pass it to write and all this stuff. It's a little not great to use. So I'd like to introduce some extra helpers that could be a little bit more, idiomatic Rust. So Tokio has a very helpful type in it for doing IO operations called buffread. Sorry, buffreader. And a buffreader, it works the same as the buffreader type in the standard library, if you're familiar with that. Essentially, what that is it wraps any kind of reader. It maintains its own buffer, and it allows you to do some higher level read operations, like, for example, read an entire line of text from a stream. So we have our buff reader, and we actually also need a string to store each line. And instead of calling socket.read, I'm going to call reader.readLine, and I'll pass it a reference, mutable reference to our line buffer. And once again, this has a extension trait that it's associated with that we need to import in order to make this work correctly. And then instead of passing buffer here, we're actually going to pass line.as bytes, because that will give us the underlying bytes from our string. Once again, if there are any questions about anything that I'm doing, please feel free to ask those immediately in the Twitch stream, and I will address those just as soon as they come up. So this is failing now because we're trying to move our socket into this buff reader, and of course you cannot move something in a loop because there's only one thing to be moved. So I'm going to go ahead and move the reader and the string creation outside of that loop so that they work a little bit better. Now we're getting an error because we are borrowing a moved value socket. So the buff reader has taken ownership of the socket, and there's now nothing. We're now not allowed to use the socket outside of the buff reader because it has that ownership of it. So how can we resolve this? The way that we can do this is using the split method on a socket. So many IO handles, they have a read part and they have a write part. And Tokio has a split method, which allows us to separate the read part and the write part so we can handle them independently as we need to in this case. Read, write equals socket dot split. And so instead of passing socket to the buff reader, I will pass the read half to the buff reader. And instead of calling socket.write all, I will call write. Let's call it writer. And this can be reader. And we can't borrow writer as mutable because it is not declared as mutable. It is now. Great. Reading out messages from the clients, reading out lines, from the client, writing them right on back to the client using a buff reader is what we've got here. And then we do still want to use this bytes read thing that comes back from read line because it's actually going to tell us if a client has disconnected or not. So if the number of bytes that we read from the stream is 0, then that actually means that the reader has reached the end of the file and there's no data left, and we just want to go ahead and exit. I'll go ahead and take out this unused import that's up here. And now we should be able to run our server and connect to client, and it still should work exactly as we expect. Hello. Glad I'm on this server. Oh, but we're getting a weird interleaving of messages here. So I typed, I'm glad I'm on this server, but I got back, hello, I'm glad I'm on this server. If I send a question mark, I get, hello, I'm glad I'm on this server, question mark. So let's send one more message, goodbye, and we get all 4 messages now. So I'll go ahead and disconnect the client. And we can see that the Rust server exited as soon as the client disconnected. But why did we get those repeated messages? It turns out that when you call read line, it actually just appends the next line that it reads onto the string buffer that you've passed into it. So this is similar to how standard library functions work. It's not really read line's job to clear out the input buffer because you might be reading in a file 1 line at a time. So if you want to have a clean string each time, it is your job to do that. So we can very easily add that in here, line dot clear. And let's try that now. Hello. So we can see now we're just getting back the single message that we send up to the server. So I will go ahead and disconnect the client, and we can see the server once again has ended. So we're handling 1 client, great. However, in order to actually do any kind of async computation or really make use of Tokio at all, because really what we're doing right now could just as easily be done with the standard library, if not more easily, since we wouldn't have await, we wouldn't have Tokio main, we wouldn't have an extra dependency. We don't start to really see the benefits until we start to get into how we're handling multiple clients independently. So if we want to handle multiple clients independently, the standard way that you do that, and the way that also we do it with Tokio, is to put except in our client handling into a loop. So, just like down here, an infinite loop for handling 1 client, we have an infinite loop that every time is just calling except to allow a new client to have access to our server. Let's go ahead and try this out. Connect, connect, connect. Hello, this works. Hello. Oh no, this one does not work. Why does this one not work, but this one does? Well, what happens if I disconnect this one? If I disconnect client 1, client 2 starts to work. Client 2 is now able to process messages. So it turns out, even though we're using this beautiful, async computation library and we're using await, we're actually not doing anything asynchronously at all. Everything we're doing here is blocking. And I know I said that async operations do not block, but the thing that async operations avoid blocking on is the thread level. However, async operations are still perfectly capable of blocking at the task level. So task is essentially a unit of work in the async world, and it's it can basically be thought of as a very lightweight thread. So these are not OS threads, they're not OS tasks. They are things, units of asynchronous computation that Tokio knows about and is able to very efficiently interleave with each other and schedule in optimal ways. So it knows how to sleep one task until its IO resource is ready, and then as soon as that IO resource is ready, wake the task up and allow it to continue processing. So right now we basically just have one single task, and that just runs through in a linear fashion exactly like any kind of synchronous program would. So what we actually need to do in order to get some kind of concurrency going on here and to get multiple clients handling and working correctly is we need to use a method called Tokio spawn to create a new task. And so we're going to wrap all of our handling for an individual client in this call to Tokio spawn. And that is actually going to move all of one client's handling onto its own independent task. And we've also added this new thing, async move here. So a lot of languages that have async and await in them have async functions, but that's basically their only unit of creating an async computation. Rust actually has the concept of an async block, which is, basically wrapping up one little piece of code into its own future, its own unit of async work. So we don't need to write this as a separate function. We could completely write this as a separate function for handling one socket, but it's not necessary. We can use this async block and pass that to Tokio spawn. Yes. So if we compile, whoops, that's not my compiler command. If we compile this and we start up a few clients, this is the second client that connected. Hello, it seems to be working. Looks like it's working for this first client too. I can send all kind of messages from both clients, and they both seem to be handled a-okay, no problem. So to summarize, recall we went from allowing one client to connect and get echoed one message back to it, to allowing one client to connect, get arbitrary number of messages sent back to it, to having a buffered reader that's using, good Rust conventions, to allowing multiple clients to connect by virtue of using a separate spawned task that's running concurrently with the task that's calling except in a loop. Any questions about anything that we had done there? Once again, please feel free to drop them in the Twitch chat, and I will answer those just as soon as they come up. So this is a great echo server. It supports multiple clients. It sends messages back to the client that connected. However, it is very much not a chat server. So communication is completely siloed. If you have 100,000 clients connected, each client will only ever receive back messages that they themselves sent. So this is it's not very good for fostering a community. It's not a chat server. So how do we get from what we have right now to having a chat server? Well, basically what we need to do is we need to communicate this line that's read from one client out to every single client who is connected right now. So the way we're going to do that is by using a type also from Tokio called a broadcast channel. And a broadcast channel, as the name implies, is a special type of channel which allows multiple producers and multiple consumers to all send and receive on a single channel. So what that means in practice is we can have a sender and a receiver on every single task for handling our clients, and each client task will send lines that it reads from its own client when they're ready. And then it will also receive lines read in from other clients as soon as they have read in their lines. So broadcast channel, accepts a single argument, which is the number of items that it can sort of keep in its internal queues for the receiver. So I need to import this, Tokio sync broadcast. And we're getting a compiler error now because it says type inside async block must be known in this context. So this is a problem because if you're familiar with how generics work in Rust, we can see this is a channel with a type parameter on it, so it can support any type of thing that is clonable and sendable and sync. So the compiler doesn't know basically what we're going to send on it. So I'm going to make this compiler error go away with just a little Turbofish telling it, hey, we're going to send strings on this channel. And now the way that we are going to use our channel is after we have read the line from the client, I will add in a call to tx.send line.clone on here. And now we are getting one of the famous Rust compiler errors, use of moved value. So this is happening very similar to when we had buff reader new inside of our loop before. This is happening because we are trying to move the value tx into this new task within a loop. So the way we get around that is by cloning tx. And this returns a result, so I'll also unwrap the result that comes back there. So we are sending items on the channel, however, we are not receiving items on the channel. So what we are also going to do in here is let message equals rx.receive.await.unwrap. Can now borrow rx as mutable as it is not declared as mutable. Okay, start with that one. Use of moved value rx. So similar to how we're cloning tx, we actually need to have a new value for the receiver on every single iteration of this loop. And I'm not sure why the API was designed like this. I'm sure they have a great reason if you ask the Tokio folks. But the way that you get a new receiver on a broadcast channel is actually by pulling it out of the sender. So we need to call tx.subscribe, and this will give us a new receiver. And that does need to be mutable. So message, it's going to come back as a string, and then we're going to change this out from line as bytes to message as bytes. So let's go ahead and start our server up, and let's connect a couple of clients. Hello. Okay, that looks good. That's interesting. So I sent how are you on client 2, but it actually received the message hello, which recall was sent from client number 1. And if I send another message from client 1, I get back that message from client 2. It seems that the sending order of our messages is very mistaken. And if we look at our logic here, it's not too hard to see why. So we're saying read a line from the client, block until you're done reading that line from the client. And then as soon as you've read the line, put something on this queue, this channel, and then immediately after you put something on the channel, sequentially after, read something off the channel and send that something to the client. Send exactly one of those things to the client. So this is a pretty odd structure if you think about it, right? Read from the client, put something on a queue, read from the same queue you just put a thing on, and then write that thing to the client. Really, this thing and this thing are both async functions that could both block an arbitrary amount of time, and really we don't want them to be dependent on each other at all. Really, we want to run those two things concurrently with each other. We want to run them at the same exact time and basically just race and see which one finishes first and act on it when it does finish. So we could accomplish this by using Tokio spawn and having a separate task which calls rx.receive and then writes stuff out to the writers. But it's a little bit more straightforward if we introduce a new concept, a new tool available to us, which is a macro that Tokio has called select. Now, if you've done any Go programming before, you're probably familiar with a select statement, and it basically just allows you to run multiple asynchronous things concurrently at the same time and act on the first one that comes back with a result. So it has its own special little syntax because it's a macro. So the way it works is you give it an identifier, you give it a future, and then you give it a block of code. And so what it's going to do is it's going to run the future. It's going to assign the result of the future to the identifier that you give it, and then it's going to run the block of code that comes after that. So we're just going to add in tx.send line.clone and line.clear right here. And then we still want to maintain our if bytes red equals 0 break thing here. So I'm just going to assign the return value of readline as result. And we're just going to say if result.unwrap equals 0, then break. Yeah. So similarly to before, this is not going to do anything concurrently yet because we just have a single thing inside of select. So the way we start to get a benefit here is once we move multiple things inside of our select statement. So rx.receive returns a future, and we can unwrap that future. Message equals, or sorry, we won't unwrap the future. Select is going to basically, it's going to do await on the future sort of implicitly as a part of the compiler machinery that it generates. And we're going to call unwrap on the result that comes out of the future. So we've got that, whoops. This line.clear goes away. This writer.writeAll moves into our select branch right here. So let's go ahead and restart our server. As it is right now. Server is running. Let's go ahead and connect up our clients. We can see that there's the hello message we typed out. There's the one we received back from the server. And we can see for the first time now, client number 2 has actually received a hello message from the server that was broadcast to it since client 1 sent it. So if I type, how are you on client 2, you can see that pops up right over here in the stream for client 1. There is an additional feature that I would like to add onto our server, which is, right now, if you type a message and you send it, you get the same message back that you sent. Now, obviously, if we were actually writing a chat server, we would not be targeting Telnet as our client software. However, in this demonstration, we are using Telnet as our client software, and so we should try and make a nice experience for all of our loyal Telnet users. So we are not going to echo the same message that was sent right back to the client who sent it. So let's go ahead and disconnect our clients, stop the server, and let's see if we can't fix the double sending problem. We have a really nice, easy way that we can do this, which is we can use the client address that accept gives back to us. Let's take off that underscore there. And we can change our call to send slightly. So instead of just sending the line of text that we read from the stream, we can also send the address of the client that it was read from. So address comes back from accept, and then address goes into the Tokio spawn, into the async move block, and it gets sent alongside the line that we read off of the network stream. And then, of course, we need to pull that off of the broadcast channel in our receiver. On line 36, we currently just have let message equals result to unwrap. Let's destructure that into message and other adder. And then we're going to wrap this right all in if adder is not equal to other adder. And of course, these types are mismatched because we told it, hey, this is a string broadcast channel. It's only going to have one string on it. We need to take this Turbofish off because it's actually going to have a tuple of string and socket address on it. So we only needed the Turbofish there because we had no calls to send. We had no calls to receive. So the compiler wasn't smart enough to, or sorry, the compiler didn't have enough information yet to figure out what kind of values are going to be sent on this channel. But now that we're calling send, we're calling receive, it has enough information to determine the types that are being used without the Turbofish. So that, let's go ahead and run it and just verify that it works all as we are expecting. So I type hello world on client 1, it shows up in client 2. 2 can go to 1. Let's see if I add in a third one here. Third client can connect and immediately its messages are being broadcast to 1 and 2. And it gets messages that are sent from clients 1 and 2 as well. And if I disconnect one of my clients, this client right here, we don't start to get, we do not start to get errors or anything like that that shows up in the stream. There's a question in the Twitch chat. What is a Turbofish? Turbofish is an operator that is pretty unique to Rust. It is essentially a way to hint to the compiler what kind of generic type you expect to be returned from a function. So if, let's come up with a really simple example of how a Turbofish might be helpful. Let's say I want to write a function that returns the default value for a type, any type. I can write that pretty easily. Give me default. That's going to have a type argument t. And it's going to take no parameters, and it's going to return a t. And we're just going to say default. Default is a trait that's in the Rust standard library, which some types have a default value, like integers default to 0, Boolean defaults to false, lists and strings default to empty collections. Most collections default to empty collections, things like this. So that just makes it easier to provide default values for your types because it's built right into the standard library. So if I add a little trait bound on here that says where t implements defaults, then it'll actually compile. And then if I try to use this, that value equals give me default, we're going to get a compiler error that says type inside async block must be known in this context, because the compiler is like, hey, this give me default function could return almost anything. There are so many types that implement default. How could I possibly know what you expect me to return? So there's a couple ways we could solve this. Like in this instance, obviously, we could just add a type annotation to the variable binding, but sometimes that that doesn't work if you're using a function call as a part of a larger expression. So another way that we can get around this is to use what's known as the Turbofish operator, which just looks like this. It's 2 colons followed by the greater than less than braces, which are used for type parameters in Rust. So this is called a turbofish because I guess it sort of looks like a fish. I guess, there's the head, there's the back of its body, and there's the tail. There's actually a fan website that somebody made, turbo.fish, that has a bunch of animations of these little turbofish operators swimming around a black screen. So that is the turbofish used for disambiguating generic types that the compiler is not smart enough to figure out by itself. I see that I provided a good explanation, so thank you. Yeah, we have a couple more minutes, and there are some additional features that we could add here. We could make this slightly more in-depth, but before we do that, are there any additional questions on anything that we talked about here? Not seeing anything on the chat, so I think we can go right ahead. So one additional change that we could make is, we could say, hey, what if this broadcast channel that Tokio provides, what if that were actually not available to us? It can sometimes be helpful to think about how we distribute messages in an asynchronous program like this. And one way that we can make that slightly more clear is to, essentially re-implement the functionality of this broadcast channel. Actually, now that I think about it, I think that may take a little bit more time than we have available to us in 8 minutes, and it may take some more explanation. So we're actually not going to do that, but I do have some additional content that we can talk about. One thing that's pretty frequently asked when seeing this program is, how do I know when to use Tokio spawn to do things concurrently, and how do I know when to use Tokio select? And this is a really valid concern that people have, because it's like, you told me 2 different ways that I can do concurrency. How do I know when one is appropriate versus the other? And a really good rule of thumb is, select is very useful when you have things that need to operate on the same shared state and you have a finite number of things. So for example, in this example, we have exactly 2 async tasks that need to run concurrently, right? We have reading a line from the network, and we have receiving on this internal broadcast channel in memory. Those are the only 2 things that are ever going to need to run concurrently, within the scope of this one task. We're never going to have a 3rd thing or a 5th thing or whatever. So select is better in this case. And in addition to just having the 2 things, we also have some shared state. It might not be obvious, but let's take a closer look. We can see that we did a split on the socket. And if we look at the type that you get back from split, you have a read half and a write half. And you may notice that the read half and the write half actually have lifetime parameters associated with them that are matched up with a mutable borrow of the TCP stream. And if we jump into the types here, you can actually see that the read half and the write half are implemented just as references to the TCP stream, the underlying TCP stream. So if we actually tried to spawn these 2 things as independent Tokio tasks, we would run into a problem, because we would be trying to split a reference across multiple tasks, which is not allowed, because anytime you call Tokio spawn, the thing that you pass into it has to be static, so it has to have no stack references in it, and it has to be send and sync. Sync does not explicitly appear in the bounds, but trust me, it has to be sync too. So I can do it. Tokio spawn async move, and we'll just make this really simple. We're just going to put this one call in here, and that's actually going to invalidate everything because it's type annotations. We now get the error socket does not live long enough, which you may be familiar with getting errors like this from the borrow checker in Rust if you've done anything more complicated than like a hello world or a FizzBuzz. This is essentially saying to us that, hey, you are calling this function down here that needs the reference to socket to be a static reference, but it's not a static reference. Argument requires that socket is borrowed for static, and it's not. So that doesn't work. It's not super explicit, but basically because of the way split works, we do have some shared state between the two branches of these in the form of the reader and the writer, which both point to the same underlying piece of memory. So it's very common in writing programs with Tokio. Like a really common pattern that I will have is a select statement that has 5 or 6 branches on it that are all just gathering messages from different channels like this, and then altering some shared state like say error counters or something like this that's part of an instance variable, something like that. So if you were using tasks for that, independent tasks to read off all those channels, all that kind of shared state would need to be behind, atomics or mutexes, things like that, so that your communication wouldn't risk a data race. But select allows that to happen, very naturally in a very sensible way. One thing to point out that is sort of a unique piece of select is the stuff that's in these branches. Line 27 can, and I can't have a multi-cursor, line 35 and line 27, those two can operate at the same time as each other. However, as soon as it jumps into one of these blocks, that's going to be the only thing that's running. So as soon as reader.readLine finishes and there's a line that's available to be acted on, it's going to jump down into this block, and it's going to suspend this future, and this future can't be executing. And same thing here, if we receive something on the broadcast channel, it's going to suspend this future, and there's no way this future can be running. So you get sort of a free, locking free concurrency guarantees just by virtue of the way that select works. And another really nice feature of select that you don't get with spawn is because it all happens on the same task, you can really easily share references between all the different branches of select. And, it just makes memory management a lot easier. You don't have to worry about making everything owned, making everything static and sync and all this stuff. Yeah. So we are just about at the time limit. So I will take another opportunity to plug my book, which is Refactoring to Rust. Refactoring to Rust, new book by Manning. It's all about making your programs more efficient without rewriting them from the ground up. Just find that one little piece of performance sensitive code, swap that with some Rust code, maybe add some glue code to figure out exactly how the two pieces are going to interact, and you'll have a much more performant program. There's a 40% off code in the link, or sorry, it's not a link, in the banner above, twitmera40. You can use that at manning.com to get 40% off Refactoring to Rust. It's in early access now. The first 3 chapters are currently available, and the 4th chapter is hopefully coming very, very soon. Thank you so much to everybody who watched on the stream today. I think it's going to be saved on Manning's Twitch channel and then Manning's YouTube page. Thank you to Manning for hosting. Also, once again, if you're looking for a job, please email me, nate@onesignal.com. We are hiring Rust developers, Go developers, Ruby, JavaScript developers, anybody and everybody. Nate@onesignal.com. Happy to talk to you about opportunities. Thank you again to everybody who watched on the stream today. I am dropping off now. Have a lovely evening, rest of the day, everybody.